Today we have Dr. Rosna Paul with us to discuss selected problems from vector spaces. Dr. Rosna did her PhD from Graz University of Technology, Austria. Dr. Rosna did her M.Sc and MPhil from Cochin University of Science and Technology, Kerala. And Rosna is a rank holder for both M.Sc and B.Sc, and also qualified CSIR Net and Inspire Fellowship. So we have a very nice person and also a very good teacher to discuss problems from vector space area. So I welcome everyone to this program, and I would like to express my gratitude to Rosna for being with Maths Aspirants. Welcome everyone to this event. Welcome, Rosna.
Thank you, sir. Thanks for the nice introduction. As he mentioned, today I would like to speak a little bit about vector spaces. Before that, I will try to share my screen. So why do we need vector spaces? That's the first question that might come to your mind when you see why should I study vector spaces. So actually, why do we need it? Sometimes when you look at the examples or in some problems, for example, in physics or in other cases, you might have seen some questions like this. Find the values of x1, x2, x3, which are real numbers, such that they satisfies the following equations. You might have already learned how to solve this kind of problems. So first, you can also represent this problem by using matrices. This is the same problem, but in terms of matrix representation. And here you consider this matrices and you know the method how to solve this. And this problem can also be written in another way, like you multiply x1 with a column vector, x2 with a column vector, and x3 with the column vector, and again this all produce another column vector. So this is the same problem which is written in a different way. And using the matrices, we can solve this type of linear equations. And if you go on with other problems, we might also see some problems which are of similar nature. For example, this problem 2 and 3. Here also we have some variables like x1, x2, x3. Here the x1 is multiplied not with a matrix as such, but with a polynomial. So you multiply x1 with some sort of polynomial of degree 2, x2 with another polynomial, and x3 with another polynomial, such that their sum is equal to some other polynomial. And here again the task is to find this coefficients x1, x2, and x3. And similar way, you also might have seen in physics or in some other subjects that find the value of this x1, x2, x4. Here in the where the variable lies has changed. Now it's in the complex space. Here it is a real space. But here the structure of the problem, if you look at the problem from a higher scale, you can see that all these problems have some variables which you have to determine, and this variable is multiplied with some sort of quotients. In the sense, sometimes it is all polynomials, or it is all matrices, or it is all these functions, which gives you something which is same as what you are multiplied with. For example, if you are multiplying with polynomials, you are looking for a solution which is equal to a polynomial. And if it is functions, it again becomes a function. And in the previous case, we have seen that if it is this column vector, it's again a column vector. So in the first case, we know how to solve this. In the second case, if you get such a problem, you might have to think about, okay, how I can solve this by using the properties of the polynomial world. In the other case, you also have to think about how I can solve it with using these functions. So instead of solving these problems separately in their world, we are creating a world which contains all these things. So we are taking, we are considering some space in which the properties of these coefficients, like this polynomials or functions or matrices, they all behave the same. So when we want to solve these problems, what we need is that we we would like to add these coefficients or multiply this coefficient with something and so on, if we know that all these coefficients behave in a similar way, then we can generate a unique method to solve all these type of problems. So instead of taking a problem in a matrix and solve it by itself, or problem in a polynomial world and solve it itself, or problems in a continuous functions and solve it itself, instead of doing it by individually, we are calling them together as a one world, and we find a solution for these problems in that world. And that world, what we call vector spaces. So before going to define what is a vector spaces, I would like to say what is a field is, because we highly rely on the field when we are defined on the vector space. So this slide might look a bit ugly, but I put it here just to give an impression of what a field is. A field is a collection of some elements or a set in which we can define two operations, which is addition and multiplication. So we not only define these addition and multiplication, but these operations satisfies certain conditions. The first one is they are closed, both under addition and multiplication. That is, if you add two elements in this set, the resulting element also belong to the set. Similar way, if you multiply two elements in your set, the resulting element should also belong to our empty set. And associativity, I think you already know. If you can associate three elements in your way, there is no rule for that. And then there is this existence of additive identity. Usually, we represent the additive identity by 0. So if you add something, this additive identity, for example, 0 to an element, you will get that element itself. Similar way, there is an existence of a multiplicative identity, which we usually represented by 1. That is, if you multiply 1 with an element, you will get an element itself. So there should exist an additive identity and a multiplicative identity. Then there is an additive inverse. For example, if you have a real number 2, you have -2. And like the multiplicative inverse, if you have 2 and we have 1/2 and so on. And the additive is commutative, because if you add 2 plus 3, which is same as 3 plus 2, and the multiplication is commutative, that is 2 into 3 is same as 3 into 2, and the multiplication is distributive over addition. So you don't have to remember all these things. So here I just mentioned this to give an impression of what is a field. We don't need any of this definition right now, but just remember that usually when you define a vector space, you need something called a field. The elements of field have very nice properties, and usually in this talk we only consider either real numbers or complex numbers. Otherwise I will mention it. So don't worry about this. So just move on. If you didn't understand anything here, but don't worry, you can still follow the rest of the talk. Okay, let's move on to the definition. What is a vector space? So vector space is a set, and the elements of the set, which we call a V, are called the vectors. And I also mentioned before, we need a field F, and the elements of F are called scalars. And with this V and F, we create some rules of how these elements in V and F behaves, and that constitutes our vector space. And for that, we need two operations. One is vector addition. And so what is a vector addition? Which means that you take any two elements in V, and we define an operation like an addition, such that V plus W belongs to V. So it is closed under vector addition. And the second operation is scalar multiplication. So here what we are taking is that we take one element from our field and one element from our vector, and when we multiply them, they should belong to our vector. So these are the main two operations we need. Not only that, we need more properties of these two operations. That is a big list of properties, but we need that. First is the associativity of vector addition. So what does it mean? That if you have U plus V plus W, then you can change this association to U plus V plus W for all vectors in V. That is the associativity of vector addition. And then there should exist a zero vector, as we mentioned in the field. So here the difference is that in the field, you are only dealing with the elements of the field, but here we have two things to remember. Some things are from our field and some things are from our vector. So far I'm talking about the elements from the vector. So in the vector, there should it should contain a zero vector, such that if you add any element from your vector space with the zero, it should give you the same vector. So zero is a representative of that element, such that u plus that element will give you same u. The next property is the existence of negatives. That is, if you have an element in V, there should exist another element which we represent by minus u, such that if you add those two elements, that is u plus minus u, you will get this zero vector. And next is the associativity of multiplication. So here, if you take any two elements from our field, which we call scalars, if you take any two scalars and then you multiply it with u, you can make the association in different ways, is that a of bu. And then there's the distributivities. So if you have a plus b, two scalars from f, and you have one vector, then you can distribute your vector over these scalars, or you also do the other way around. If you have a scalar and two vectors, you can also distribute them. And the last one is kind of this. The previous case we said a multiplicative identity, but here we call it as unitarity, because our vector space, so we are taking a scalar and then we have a vector space. So 1 times u equal to u for all u belongs to u. And apart from these main things, there are some properties we can check. That is, for any zero in your scalar, then the zero times your vector will be always zero. This looks very trivial, but this is a one property of a vector space. And the previous case we mentioned about the identity, additive identity, which is our zero vector, this will be a unique one in our vector space. And also the additive inverse, that is the existence of inverse. For example, if you have a vector and it has an inverse, then that inverse will also be unique. And the other property is that if you multiply some scalar with our vector and gives you 0, then either c equal to 0 or x equal to 0. So these are some normal properties you might see in real numbers. But I mentioned this sometimes in problems they ask, okay, whether this is true or not. So that's why I put some properties. So let's see what are the examples. So as I mentioned before, real numbers are one of the examples of vector spaces too, because if you take any real number over a field as a real number, so you take a vector space of real numbers over the field of real numbers, you can see it satisfies all the properties with our normal addition and multiplication. And the next set you might have seen many times is the set of polynomials. So real polynomials, which means that you take the collection of polynomials where the coefficients belongs to the field of real numbers. And if you take a polynomial of degree n, you know how to add two polynomials. And the scalar multiplication is, if you have x raised to n, then 3 times x raised to n gives you this scalar multiplication. So if, you can check all the previous properties and it satisfies everything. And here the 0 vector is nothing but 0 x raised to n plus 0 x raised to n minus 1 and so on. So it exists. And set of all matrices. So if we have n by n matrix, you can add two matrices and you can multiply each element of matrix by a scalar, so which gives you the scalar multiplication. And so this gives you a small question. So if you understand so far what I'm talking about, you might be able to answer this question. Let's see. The question is that let V be a set of all pairs of real numbers and F be a field of real numbers. So it's nothing but R2. And we define a special addition over R2. That is x plus y. If you take any ordered pair xy and another ordered pair x1, y1, we add it in such a way that x plus x1 comma 0. So whenever you add two elements from your R2, you will get x1 plus x plus x1 comma 0. And the scalar multiplication is defined by cxcy gives you, sorry, the c should go inside, cx0. So that's my mistake. So cxcy gives you cx and 0. So now that is how I define two operation. Is this vector space V of set of all real numbers, or the ordered pair of real numbers, a vector space over the field of real? So what do you think about this example? Is it a vector space or not? You can answer in the comments. Let me try to see whether. So what do you think? Does it satisfy all our properties or not? Okay. Chadas is not a vector space. Does somebody else have a different opinion, or does everybody agree? I will wait for a few more seconds just to make sure that everybody had tried it. Let me see. Okay, let's see. So most of you got it correct. Okay, so I go with very easy case. Let's check what about the additive identity in V. So you also talked about other things, but that's good. So here I'm looking for additive identity. For example, this vector space has an additive identity and we call it as AB. Then we know that if you add this additive identity with xy, then it should give xy for all values of x and y in R. But by our addition, this is the result we should get. So which means that when you add these two, you should get x plus say 0, which should be equal to xy. By comparing the two ordered pairs, we can see that y should be equal to 0. So if there exists an additive identity, the y should be equal to 0. But we cannot always say that in xy the y is 0. So if you take, for example, 1, 2, then there is no then you cannot compare it with this additive identity. So which means that an additive identity does not exist in this vector space. So if there is no additive identity, then you cannot make it as a vector space. So your answers are correct. Very good. I hope that you understood the definition of vector spaces. Okay, then next thing is a subspace. So if you have a big vector space, then how can we call something as a subspace of this vector space? So here, let W be a non-empty subset of a vector space, and W is said to be a subspace of V if W itself is a vector space under operations induced from V. Which means that there should be an additive identity in your vector space, and if you take any two elements from V, it should be closed under two elements from W, it should be closed under W, that is their sum should belongs to W. And for any scalar from F, and if you take any vector from W, then their product should also belongs to W. And checking all the properties of the vector space, whether it is a subspace or not, is a bit lengthy. So we can make it as a very small note. Check whether there is an identity, and then if you take any two elements from W and any two scalars from F, just check whether AW1 plus BW2 belongs to W. So I think this is easy to remember. And let's take an example. I hope that many of you might already know about subspaces. So before giving that answer directly to this question, I will let you do the, so those who know about the subspaces and doesn't need an example done by me to understand it, please try to solve this question. That is, which of the following is or are the subspaces of f of x? So here f of x is the set of polynomials over the field f. W1 is the collection of all those functions such that f of x plus 1 equal to f of x, and W2 are all those functions such that 2 times f of 0 equal to f of 1. So the question is whether this is a subspace, W1 is a subspace, W2 is a subspace, both or neither. For those who already know about subspaces, can try this question and then I will explain the solution. What do you think about W1? Does somebody check what happens with W1, whether it is a subspace or not? I haven't received any answers yet. Maybe it's taking time, or did you? Is it confusing to check it?
Option A, it is not a subspace, but checking for the option B once.
Okay. Maybe I will start with W1. So if you are confused with next one, you can try the same method. Okay, let's take the first vector space. So you are taking the collection of functions such that f of x plus 1 equal to f of x. And here, if you take two elements from W1, I call it as f of x and g of x. And I take two scalars from our field f. And what we have to, and since f of x and g of x belongs to W1, we can say that f of x plus 1 equal to f of x and g of x plus 1 equal to g of x. And what we have to do is that I want to find this function, that is a times f of x plus b times g of x, and I call it as h of x. I want to see whether h of x belongs to W1 or not. For that, h of x is just a f of x plus b times g of x. We know that f of x is same as f of x plus 1. You can replace it with x plus 1. And g of x can be replaced by g of x plus 1, which will give you h of x plus 1. So here h of x is same as h of x plus 1, which is what we have here. So it satisfied this condition. So it is closed under addition and scalar multiplication. And if you take any zero polynomial, then for zero polynomial, 0 of x plus 1 is same as 0 of x. So that also belongs to W1. So actually W1 is a vector space. Is that clear?
Yes, ma'am.
Okay, then can you try the next one, W2, in the same way? So we use the same method. We take two elements, f and g from W2 and two scalars. And by the property of f of x, we know that 2 times f of 0 equal to f of 1 and 2 times g of 0 equal to g of 1. And first thing, we can also check whether there exists this additive identity. For example, if you take a 0 vector, 2 times 0 vector is same as f of 0 of 1, which is again 0. So that will not make any issue. Only we have to check whether this a times f of x plus g times b times g of x belongs to our W2 or not. So how do you check that? The condition that it belongs to our field is nothing but satisfying this case. So let's check one of these. For example, what happens 2 times h of 0, which is nothing but 2 times this whole thing, which is a times f of 0 plus b times g of 0. F of 0, we know that this is f of 1. Sorry, I first take the 2 inside, and then 2 times f of 0 is nothing but f of 1. I can replace it by f of 1. And 2 times g of 0 is nothing but g of 1. And this gives you the definition of h of 1. So if you have 2h of 0, this is equal to h of 1, which satisfies the condition here. So h of x belongs to W2. So in this case, both h of W1 and W2 are the subspaces of our polynomial vector space. So actually the option C is correct. So if it is a question of B part, like only one answer is correct, then C is correct. If C part, sometimes they also want these two things to be also marked. I hope this is clear. Okay, let's move on to a next question. If V is a real vector space of all mappings from R to R, so this is a functions from R to R, and V1 is a collection of those functions such that f of minus x equal to f of x, and V2 is the collection of functions such that f of minus x is equal to minus of f of x, then which of the following is correct? So the options are neither V1 nor V2 is a subspace of V. Next one is V1 is a subspace, but V2 is not a subspace. C is the reverse. That is, V1 is not a subspace, but V2 is a subspace. D, both V1 and V2 are the subspaces of V. So clearly, only one of the option is correct. So what is the correct answer?
Ma'am, option D, both are
Option. Yes.
Both are subspaces.
Let's see what others also say. Okay, we got one answer. Answer D. And if you got any answer, you can also write it in the messages. So you can try to read.
Ma'am, I think V1 is a subspace, but V2 is not a subspace. I'm looking it like if we multiply to odd function, it may be a even function, so it doesn't belong to V2. So V2.
Yeah, there is one. There is an issue in that multiplication because you are multiplying two elements from a vector space. But here we only need a scalar multiplication. So if you are multiplying, you only take some scalars from R and then multiply it with the function. So we are not multiplying any two elements of the vectors. We are only multiplying a scalar with a vector. For example, if you have to multiply a function, you can multiply it with 3 or 4, but you are not multiplying f and g.
Okay, got it.
So there are many people who said that its option is D. Okay, maybe I will try to explain this. Let's see. We take the first vector space, which is the collection of functions such as f of minus x equal to f of x. and we let h of x as before, the linear combination of two elements from V1, and it is a direct application. You just look what is h of minus x is, which is nothing but a of minus x plus b g of minus x, and f of minus x we know what is it is, so it is f of x and g of x, and this is nothing but h of x. So here you will get h of minus x is same as h of x. So this h of x belongs to V1, so it is a vector space. V1 is it is a subspace. And the next one is very similar as the same. You take this h of x and you calculate what is minus h of minus x is. But here the only difference is that f of minus x is minus f of x. You have to take this minus outside, which is nothing but minus of a f of x plus b g of x, which is minus h of x. But this is the condition we require. What we require is that f of minus x should be equal to minus of f of x. So our h of x, which is this linear combination, satisfies this condition. So V2 is a subspace. So you are all right. D is the correct answer. Okay, I hope that you understood the concept of subspaces. Now let's move to the next set of definitions. If you have a vector in your vector space, and this vector is said to be a linear combination of other vectors, for example, v1, v2, vk, this means that there exists some scalars, this is ci, there exists some scalars ci's from f such that v can be written as the sum of ci vi. So if v is said to be a linear combination of other vectors, which implies that there exists some scalars such that v can be written as c1 v1 plus c2 v2 plus c3 v3 up to ck vk. So in that case, that is called the linear combination of vectors. And if you have a set of vectors in our as a subset of our linear space, and this set of vectors are said to be linearly dependent, if there exist some scalars from our field f such that when we write this c1 v1 plus c2 v2 and so on, which is equal to 0, when you have to make this equation equal to 0, not all ci's should be 0. So which means that not all coefficients should be 0. So in other words, what it is saying is that if you have a collection of vectors, then they are linearly dependent, which means that one of the vector can be written as the linear combination of the others. And if it is not the case, for example, this is not all 0, then they are called, this is all 0, then they are called linearly independent. So if something is not linearly dependent, then it is linearly independent. So that is the condition. So I will explain it once again. If you have a collection of vectors, and when if you're able to write a linear combination of this collection of vectors equal to 0, that is, if a 0 can be written as the linear combination of these vectors without making all of these coefficients ci's 0, then they are linearly dependent. If we can only write this in this way, with all the ci 0, so only possible way to write this is to make all the coefficients 0, then they are linearly independent. I hope that I didn't make you confused. Maybe let's try an example to make sure that you are not confused with the definitions. The example is that so the question is that which of the following is or are linearly independent set of vectors in R3? Those who are understood the definition, please try it. Otherwise, I will also explain it afterwards. So once again, linearly independent means that if you want to write it as a linear combination, which is equal to 0, all the ci's should be 0. If one of the ci's is not 0, then they are linearly dependent. Okay, I guess this is clear. That's it. Maybe I will start with one to get an idea of what I'm doing.
Ma'am, option A and B.
Okay, option A and B. Let me see. Okay, first we can check whether option A is correct or not. So here we have three vectors. I want to see whether they are linearly independent or dependent. For that, I want to take the linear combination of them equating to 0. So I take A time multiplied with 1, 0, 0, B multiplied with 1, 1, 0, and C multiplied with 1, 1, 1, which is I'm equating to 0, 0, 0. So you know how to do this scalar multiplication. So you will get this one, BB0, CCC. And you add all the, so how do you add three vectors here? So the first element is A plus B plus C, and the second is B plus C, and third is just C. And now you have to equate this together with A. So and our aim is to find the values of these coefficients such that this how this this equation is solved. So here when you compare these two vectors, you can easily see that C equal to 0, that is clear. And here B plus C equal to 0, but we already know that C is 0. Then the only possibility is that B equal to 0. Now we have B and C x 0 and A plus B plus C equal to 0, which means that A equal to 0, B equal to 0, and C equal to 0. So if the only possible way to equate this side with the right hand side is to write A equal to 0, B equal to 0, and C equal to 0, which means that this set of elements are linearly independent. So you're right, A is a collection which is linearly independent. So I couldn't see who is still you, but in the chat, Sneha, Anil, and Anamika have said that A and B. Okay, did you all agree that B is also linearly independent? Okay, let's check B also. So in B, we have again three vectors, and we use the same method. We try to evaluate the coefficients A, B, and C such that this equality holds. And while doing the scalar multiplication and adding, you can see that the first entry is A minus B, which equal to 0, and the second one is A minus 2C equal to 0, and third is A plus B plus C equal to 0. So A minus B equal to 0 means that A equal to B, and here we get a C equal to half of A, which is equal to B, and here you can substitute the values of A, B, and C. So the first case, and half of B equal to C, then A is nothing but B, B is B, C we know that is half of B, then altogether we get 5 by 2 of B equal to 0, which implies that B equal to 0. So when B equal to 0, then obviously C is also 0 and A is also 0. Then we get all the coefficients as 0, which implies that the given set of vectors are linearly independent. So you are right, A and B are true. Then what about C? So first I will go by this long method, but if you are more familiar with the vector spaces, you can say it immediately why it is dependent. So let's go with the long method. So we do the same method. We multiply each element with some scalars and equate it to 0, 0, 0. And when you equate all the equation we get here, we will get C equal to D, A equal to 0, and B equal to minus 2D. So from here, it is clear that not all coefficients are 0. For example, you can put D equal to 1. Then what we get is that C equal to 1 and A equal to 0, B is equal to minus 2. So there exists some collection of coefficients. Not all them are 0, but if you substitute these values to here, you will get 0, 0, 0. So which means that these elements are linearly dependent. So third one is wrong, hence the fourth one is also wrong. The other easy method to look at this problem is that if you have a vector space of R3, then the maximum number of linearly independent, the size of the maximum linearly independent set is 3. So if you take any collection of 4 vectors from R3, then they will be linearly dependent. So this is the easy method to consider the case C, but since you are only studying in this way, it's for the first case it's easy to see it in a direct way, but later you can see that for R3, 4 elements will not make it as a linearly independent set. So I hope that you all understood. Your answers are correct. Yes. So next, let's move on to the next theorem. This is a theorem which we widely use for looking at the linearly dependent or independent set. And I also mentioned this just before. That is, if you have a collection of linearly independent sets, then one of them is a linear combination of others. So whenever you have to check whether one set is linearly dependent or independent or not, then you can check whether any of them can be written as a linear combination of the others. For example, in our previous case, we have seen that this set is not a linearly independent set, which is a dependent set, which means that one of these elements can be written as the linear combination of others. So let's check which one. For example, if you take this 0, 1, 0, then it can be written as the linear combination of 1, 1, 1 and minus 1, 1, minus 1 in this way. So one can be written as a linear combination of others. So that's why this set becomes linearly dependent. So then next question might rise from here is that we have said that if you have a linearly dependent collection, then one of them can be written as the linear combination of others. So can we choose them arbitrarily? So from a given collection, I know that this collection is linearly dependent. Can I pick any of them and say that, okay, this is the one which is a linear combination of other? Is it possible to write any vector in this linearly dependent set as a linear combination of others? What do you think? I hope the question is clear. That is, if you have a collection of a linearly dependent vectors, you know that this collection is linearly dependent. Then from this theorem, there exists at least one element which is a linear combination of others. So here I picked 0, 1, 0, and I say, okay, this can be written as a linear combination of others. So can I pick just something else? Can I arbitrarily pick one, and can I write it as a linear combination of others? What do you think? Sneha had said that we cannot, and Elizabeth has said yes. Okay, there is a confusion whether it is possible or not. Let's give you an example. Actually, we cannot select this as arbitrary. For example, if I take R2 and my vectors are, I let E1 as 1, 0 and E2 as 0, 1, and my collection of vectors are E1, E2 and 2 times E1. So this is clearly not a independent set, because this linear combination gives you 0, where not all coefficients are 0. So this is a linearly dependent set. But here, if you try to write E2 as a linear combination of E1 and 2E1, this is not possible. So if you have a linearly dependent set, not all elements can be written as the linear combination of the others, but there should exist at least one which can be written as a linear combination of others. Yes, I guess most of you are understood. Okay, let's take another small question. This is not that difficult. The question is, consider a vector space V over the field of real numbers spanned by the following set. Then what is the dimension of V? Okay, here I have to mention what is the dimension first. I think I have mentioning it before. Sorry, this question has to come later, but I will give an idea. So you have a set S, and this set S is spanning your vector space. And a basis of a set is a basis of a vector space is a set which should be spanning and which should be linearly independent. So if a set is spanning, then either that set, if it is a linearly independent set, or a subset of it, which gives you a linear independent set, is a basis of your vector space. And the number of elements in a vector space gives you the dimension of your vector space. So here what the question is that you have S, and we know that these are the elements that spans your vector space. And the question is how many linearly independent elements are in the set S, which is the other way to say this question. So you have a set S, and what is the number of linearly independent elements in the set? Answer is C first now. Okay, let's see. So how can you say this? The one possible. So if you want to say something is linearly dependent and you want to get rid of it, you have to check whether that can be written as the linear combination of the rest of it. So whichever elements which can be written as the linear combination of the remaining things, you can get rid of it. And by taking out all those cases, what you left will be a linearly independent set, and the number of elements in that set will give you the dimension of it. Okay, there are many answers. Aminta, if I'm calling that correctly. Sneha, Aparna, Anila. Okay, all set 3. Okay, then let's check the answer. Okay, Ravi Kumar. Yes, we are getting more answers as 3. Okay, let's check. So we have a set S, and it is already said that it spans our vector space, and it has 1, 2, 3, 4, 5, 6 elements. So our dimension of vector space is at most 6 because we have only 6 elements here. And now let's check which all of them can be written as the linear combination of other. For example, if you take 1, 1, 0, 0, it is clearly can be written as the combination of 1, 0, 1, 0, 0 and 1, 0, 0. So you can get rid of that. And next I take 1, 0, 1, 0. So it can be written as a linear combination of 0, 0, 1, 0 and 1, 0, 0. So this and this. So you can get rid of this element. And if you take 1, 1, 1, 0, it can be written as a linear combination of 3 elements. Then you can also get rid of it. So if we take away this one, and this one. So the remaining is these 3. But these 3 cannot be written as a linear combination of any of the others. You can check that if you want to. But here you can see this subset of S is linearly independent set. So this forms actually the basis of our vector space. And since it has only 3 elements, the answer is 3. So all of you are correct. Yes, Anamika, Lakshmi, Elizabeth. Yes, everybody is correct. So I hope that you understood what is linearly dependent and what is linearly independent. Okay, this question actually came a bit before I define a basis. So maybe you already got an idea what is the basis is, but I will give you a formal explanation of what a basis is. A set of vectors in a vector space is said to be a basis if every vector can be expressed uniquely as a combination of a linear combination of these vectors. In other words, we can also say that if a vector is expressed as a linear combination like CIEI and also AIEI, then you can always say that CI is equal to EI. So we can always express every element uniquely as a linear combination of these elements. And this basis is always a linearly independent set. So in other textbooks, you might also see the definition of basis as a set of elements which are linearly independent and spans your vector space. So that is also true. The main property of the basis is that every element can be written as the combination of elements from the basis, and this is also a linearly independent set. And if a vector space has basis of n elements, then any set of n plus 1 vectors is linearly dependent. So that is what we saw in a example before. If you have R3, then the number of elements in the basis of R3 is 1, 0. So it's 3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. So these are the 3 basis element of R3. That's why the dimension of R3 is 3. But if you have one more element in your collection, that is, if you have 4 elements in your set, then that will be always be linearly dependent. So that is the case here. Okay, I hope that you already understood the definition. This is not a difficult definition. A basis means that every element in your vector space should be written as the linear combination of basis, and the elements in the basis are linearly independent, and number of elements in the basis is the dimension, which also this definition also come later. So these are the main takeaways you have to you can take from the previous slide. With this information, can you answer this question? That is, let V be a vector space over a field F of dimension n, which means that in a basis of V there exist n elements. Then consider the following statement. The first one is every subset of V containing n elements is a basis of V. I already told you that basis has n elements because V is of dimension n. So it's the reverse case. Thus, every subset of V containing n elements forms a basis of V. The second statement is that no linearly independent subset of V containing more than n elements. So which of the above statements is true? So I think I'm getting answers. Only second one is true. Option B, Anamika and Parvati. Okay. I actually forgot what is the starting. Okay, Elizabeth and Aminta. I guess the name is correct. Sneha, Fasna, Aparna. Okay. So most of the people are saying the B, option B is correct. That is only the second one is correct. Yes, you are right. Because if you take a collection of n elements and that collection doesn't means that is linearly independent. For example, you can take a collection for R3 as 100, 200, and maybe 300. So this is a collection of 3 elements for R3, but all of these are linearly. So this collection is linearly dependent because one is a scalar multiplication of others. The second one is no linearly dependent subset of V contains more than n elements. Yes, that is true. That is actually what we said just before. If we have a basis of n elements, then any collection of n plus 1 is linearly dependent. So linearly independent set cannot have more than n elements. So option B is correct. Yes, I think all of you got it correct. Okay. Now we are so we are taking the same, just giving some definitions again, which I already mentioned before, but let's go it in a more formal way. Let V be a vector space and assume that V has a basis consisting of n elements. Then if you take not only just taking any collection of n elements, but if you are taking linearly independent set of n elements, n vectors, then it forms the basis of V. And then a vector space is said to be a finite dimensional if there exists a finite subspace such that I'm audible. A vector space V is finite dimensional, which means that you have a subspace S such that it forms a basis, and this basis contains only finite number of elements. So that is the conclusion of this statement. And this I already mentioned, a dimension of a vector space is nothing but the number of elements in the basis. And this can be uniquely written as, so if we have n elements in your basis, then they can be uniquely written as in this form. And usually when we define dimension of a vector space, it is denoted by dm of v. So if we have a dimension n, then dm of v equal to n. So this is mostly repeating the things which I already mentioned before. Okay, then there are some properties for the basis, which sometimes ask for CSI questions. Can we do this or do that kind of questions? So the first one is that let B be a vector space of dimension n, and let W be a subspace of V. Then any basis of W can be extended to a basis of V such that Vi equal to Wi for all I up to K. So if you have a vector space and a subspace, and if you know that we have a basis of this subspace, then you can always extend this basis to a basis of a vector V. And that is the nutshell of this paragraph. And the another property is that if you have a vector space and you have two subspaces, which is W1 and W2, then the dimension of W1 plus W2 is equal to the dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So this formula also sometimes asks for the questions like if the dimension of W1 is 2 or dimension of W2 is 4 or something, then what can be the dimension of W1 plus W2? So these questions can be answered by using this formula. Okay.
Ma'am,
Then,
excuse me.
yes.
Ma'am, in the previous slide for the first result, can you give an example for it? Like how it will be applied in the question?
Okay. For example, if you have a collection of symmetric matrices, then what you know is that only the elements of the upper part of the triangle. So how I can show that? So what are the bases of such? If you have a symmetric collection of a symmetric matrices, then the basis of the symmetric matrices is 1, 0, 0. So the first element is 0, 1. Second element is 1. Then the next one has the third element 1, and so on. So this gives you only the, for example, if you have matrices of size 10, then the number of elements in this basis is just 10 times the sum of the first 10 elements. But if you want to extend it to the real to the whole matrix space, you need to add more vectors into it. That vectors is the vectors which are in the remaining spaces. Okay, that is more complicated to say without writing. Let me think about some small examples. If you consider, for example, some polynomials on n polynomials of degree n, and if you ask to if you have a subspace which has some properties that there is no constant, or there is no something, there is some properties in the following in that subspace, and you only know the basis of that small subspace, then if they ask you to find the basis of the whole polynomial thing, you can just look at what are the missing basis, and you can add it to your collection. So in this way, you can extend it to the whole system. Is that clear? I think I'm a bit vague with the answer. Okay, let me think about that question, and I will give you a more precise answer. So the main actually is that if you know the basis of your smaller subspace, and you ask to look at the basis of the larger one, you can keep that basis of the smaller subspace as itself, and you only have to add the remaining basis for the larger one, because the basis is not unique for a vector space. A vector space has a different, if you take R3, then there is different ways to write the basis. So, but if you want to get a basis of a larger one, if you already have something for a smaller subspace, you can build on that. You don't have to do it from a scratch, but you can take the smaller subspace at the basis of the smaller one as itself, and then you can add elements to it to make it bigger. Let me think about, so right now I'm not remembering any direct questions of this, but let me think about it and let you give your correct question. So I hope that you understood the idea of this statement, but I will give you a correct question that can be asked in the competitive exams. Sorry for the
Yes,
confusion.
ma'am. Okay.
Okay, let's try this question. So consider the vector space W1 with this property and W2, then which of the following are true? Could you try this? And I will be back in a moment because my battery is running out. Just a moment. Okay, I'm back. Did you get the answer? Or am I muted? Can you hear me?
Yes, ma'am.
Yes,
Okay.
ma'am.
Okay. Did you get the answer? Okay, I meant to answer A. Sneha answer A. Hilary answer A. Okay, I think most of you are getting answer A. Let's check. So first we consider our vector space W1 is the collection of all vectors in R3 such that x plus y plus z equal to 0. So how do you consider a basis of W1? So if you put x equal to 1, then you need y plus z should be 0. So if x equal to 1, you can make either y equal to -1 or you can make xz equal to -1. So the other possibility is that you put y equal to 1 and z equal to -1 and this is 0. So why that is not possible? Because if you have 0, 1, -1, so you put y equal to 1 and z equal to -1 and 0. If you take the sum, it gives you 0. So this can be an element of basis, but why we are not taking it into the basis? Because this can be written as the linear combination of these two. So basis should be always be linearly independent. So the basis of W is nothing but this set, and it has dimension 2. Then what about our next set, that is W2, which is the collection of elements from R3, such that the first element is X and second is Y and third is minus X minus Y. So here again,
Rosna,
yes.
Could you please restart sharing, because I think some issue with that.
Okay.
It's for recording purpose. It is not in the full screen. That's why. Okay.
Okay. So can I try it once again?
Yeah.
Now can you see it?
Yes, yes.
Okay. So now we consider the vector space W2, which has basis this one. You can obtain by in the same way by putting some values to X and Y. If you put X equal to 1 and Y equal to 0, you will get 1, 0, minus 1. And if you put X equal to 0 and Y equal to 1, you will get 0, 1, minus 1. So again, it has dimension 2. But if you observe these two vector spaces, you can see that both of them has same basis. So basis of W1 is 1 minus 1, 0, and other 1, 0, minus 1, and it is same as here. So it's not a coincidence, it's actually the same vector space, because if you take W1, the condition is that you have 3 vectors such that X plus Y plus Z equal to 0. And if you make this set equal to minus X minus Y and put here, then you will get XY minus X minus Y, which is nothing but W2. So basically these two are the same subspaces and they have dimension 2. So option A is correct. Option B is not correct because they have the same dimension, so it should be equal to 0. And C is also not correct because dimension of W1 is 2, dimension of W2 is 2, their sum is 2, but the dimension of R3 over R is 3, so 4 and 3 is not equal, so most of you are correct. Okay, then let's consider a question from the CSIR net paper. The dimension of a vector space for all symmetric matrices of order n by n with real entries and trace equal to 0 is A, n square minus n by 2 minus 1, B, n square plus n by 2 minus 1, C, n square minus 2n by 2 minus 1, and D, n square plus 2n by 2 minus 1. So what do you think about this question? Okay, most of you got option B. Can someone tell me why you consider option B? Many of you have mentioned option B.
Ma'am, because number of non-trivial entries in symmetric matrix are n into n plus 1 by 2. If n is the size of the matrix, and here there is one linearly independent restriction, that is trace is equal to 0.
Yeah.
So that's why we subtracted 1 from result.
Yes, you are correct. Okay, then I have some set of other questions. Before that, I have to change the screen. Let me try to stop there and I will share the next questions in a moment. Sorry, due to some time constraint, I couldn't prepare everything on the LaTeX slide. So the rest of the questions will be handwritten. So I'm audible, right? And you can see the screen.
Yes.
Okay. So the answer is correct. So here, if you take the symmetric matrices, for example, if you're taking some 3 by 3 matrix in general, then the basis of this matrix is nothing but 1 0 0 0 1 0 0 and so on. So you will have a basis of basis containing n square elements. But when you are considering the symmetric matrices, here you can see that the B element of the second entry is same as that of this one and so on. So you only have to consider the elements of this part. For example, in a 3 by 3 matrix, you only have to consider the elements 3 plus 2 plus 1, which is the sum of elements up to 3, the sum of the numbers up to 3. And here there is an additional condition that the trace is equal to 0. That is D plus A plus D plus F equal to 0. So you have you can replace one of this element by the linear combination of others. So in total, instead of this number, you can take one more element reduced because one of them is linearly dependent. So the total number of independent variables is 5, and the total from for the 3 by 3 case, you have the total number of the bases have 3 into 3, which is 9 elements, and out of which only 5 of them are linearly independent. So in this way, if you look at the whole set, you can consider you can get the option. So that was correct. This moment is not. Okay, let me try to squeeze it a bit. So can you see the next question?
Yes, ma'am.
Okay. So the next question is, if you have a collection of linearly independent set, then which of the following set are linearly independent? So I'm giving you a collection of a linearly independent set. Then I create some other set based on this linearly independent set, and which of the following are linearly dependent? And this answer and the options are A, B, C, D. In A, I am subtracting two vectors, for example, v1 minus v2, v2 minus v3, and so on. And in option B, I'm adding some vectors, that is v1 plus v2, v2 plus v3, and so on. And in C, I'm multiplying some scalars to these vectors, for example, v1, 2v2, 3v3, and so on. And also in D, I'm using the same method by multiplying different scalars. So which among these will be again linearly independent? Option C and D. Shika, C and D. Okay. Elizabeth, C and D. Sneha, C and D. Amenta, C and D. Okay, so I'm getting a lot of results about C and D. Okay, let's check each case separately. So, for example, when we consider A, we have v1 minus v2, v2 minus v3, and so on until vn minus v1. So, in order to deal with the set, let's let that n equal to 3. So, in that collection, we have only these many elements, that is v1 minus v2, v2 minus v3, and v3 minus v1. But in this collection, you can easily see that v3 minus v1 can be written as the linear combination of v1 minus v2 and v2 minus v3. So A is linearly dependent. So option A is wrong. Now let's consider B. So here also I consider a small case. For example, let n equal to 4. Then our collection in B have reduced to V1 plus V2, V2 plus V3, V3 plus V4, and V4 plus V1. Again, you can see that V1 plus V4 plus V1 can be written as the linear combination of the remaining vectors. So they are again linearly dependent. Now what happens with our case C? It's jumping very fast. Okay. For the case, for the option 3, we have the collection of the vectors V1 to V2, 3, V3, and so on. If you want to say that they are linearly independent, you have to look at the linear combination of them with 0. So for that, I take C1 V1 plus C2 of V2 V2, C3 of 3 V3 up to Cn of Vn NVn, which is equal to 0. But here you can see that the C2 and 2, these are all from the scalars, from the vector field, the field. So I can combine them into a different scalar from the field. So I call them collectively as C2 dash. In the similar way, I call them as C3 dash and up to Cn dash. But we know that the collection of the vectors v1 up to vn is linearly independent set, which means that if you write all the vectors of this form, then all of the ci's here should be 0. So every one of this should be 0. So c1 equal to 0, c2 dash equal to 0, and so on, which means that c2 dash, which is nothing but c2 times 2 equal to 0, implies that c2 equal to 0. In this way, when all these coefficients are 0, which implies that the other coefficients like c2, c3 from here, they are all 0, which means that this collection of vectors, that is v1, 2v2, 3v3, and nvn up to nvn, they are all linearly independent. So the option C is correct, and most of you are said it is correct, yes. And with the same argument, so because it's basically looking in the same way, here instead of 1, 2, 3, 4 up to n, they are putting in the reverse order, n minus 1 up to. So it's just multiplying your vectors with some scalar coefficient, then you will get again a linearly independent set. So C and D are the correct options. Yes. Okay, let me try to zoom it a bit. Just a moment, let me try to zoom. No, second. Okay. I think this is the maximum I can zoom here. I hope that that question is clear. The answer is C and D, and most of you corrected it. Now I'm moving to the next question. Let V be a collection of vector spaces of matrices such that if you have a X, then AX equal to XA is a set of matrices that are commuting with A, where A is a square matrix such that A is 1, 0, 0, 0, 1, 0, 3, 1, 2. Then this collection of matrices which are commuting with A is not a vector space. B, it is a vector space but with dimension 5. C, it is a vector space with dimension 3, and D is a vector space with dimension 4. So let's see. Okay, Sneha says option C. Rosna says it's C. So I hope you at least got that this is a vector space. Okay, let's see. So first we have to check whether V is a vector space or not. For that, I take two elements from V from the vector space, and I know that if they belongs to V, then they commutes with A. So xa equal to ax, so ax equal to xa, and ay equal to ya. And I'm doing this scalar multiplication and adding in two different ways and two different steps. For first case, I'm checking whether it is closed under addition. That is whether x plus y. So if xy belongs to V, whether x plus y also belongs to V. So in order to check whether x plus y belongs to V, I have to say whether x plus y commutes with A. For that, I take A times x plus y, so that is ax plus ay. By using this equalities, I can get back to x plus y times A, which means that x plus y belongs to V. And for the other case, you need a scalar lambda. Then A times lambda x is nothing but lambda times ax. And when you replace ax by xa, we get lambda x times A. So it is also closed under scalar multiplication. So V is a vector space. So the first option is wrong. V is a vector space. Now I have to find the dimension of my vector space. So how to find the dimension? To get an understanding of the dimension, I want to know what my vector space, the elements of my vector space look like. So our condition is that our vector space should be commutable with the matrix A. So for example, if I take any 3 by 3 matrix, A, B, C, D, E, F, H, I, G, H, I, and I want to multiply it with my A. So when I multiply it with A, I get this matrix. And since it is commutative, I also want to multiply in another way. So it is XA, and this is AX. And if I multiply it in this way, I got this matrix. And I know that this XA and AX are same, which means that these entries are same as these entries. So A plus 3C is equal to A, B plus C equal to B, 2C equal to C, and so on. So by equating these entries, I get this set of equations. Here you can see that my condition is that 2C equal to C. So this happens only if C equal to 0. So clearly I get C equal to 0. And here 2F equal to F which means that F equal to 0. So C and F becomes 0. And now here the C and F equal to 0. Here B equal to B and E equal to E, which doesn't give you anything else. And here also C equal to 0 and F equal to 0, which means that A equal to A or D equal to D, which again also didn't give you anything. Then only we can, other cases, G plus 3I equal to 3A plus D plus 2G. So here I can cancel G from both sides, and that will give me 3I equal to 3A plus D plus G. And writing in terms of G, I will get 3I plus 3A plus D. So here a G can be written as a linear combination of I, A, and D. In the similar way, I consider this H. So here also I cancel H, and from the remaining H, I can write it as a linear combination of I, B, and E. So here G and H can be written as the linear combination of the rest of the things. So in that case, is there any confusion? Okay, so here I get C equal to 0 and F equal to 0. A, I don't know any other further information. B also, D also, I don't know anything else. E also, I cannot say anything. And instead of G, I can write G as 3I plus A minus D, and H as I plus minus 3B plus E, and here I have I. So what are the number of variables here? So I have A, B, D, E, and I. So there are 5 variables which we want to consider. So the dimension of V equal to 5. Okay. Then the next question is, let V be a finite dimensional vector space and W1, W2, W3 are subspaces of V. Then which of the following are always a subspace of V? Option A. Option A is W1 union W2 intersection W3. B is span of V minus W. So you're removing the elements from W1 from V, and from that collection you are taking the span of it. And C is W1 plus W2 union W3. And D is W1 intersection W2 minus W3. So you are removing all the elements from W3 plus from W2, and you are taking that set intersection with W. So which of the following are the subspaces of V? There is a doubt whether it is a B. Okay, Elizabeth is saying B and Shika is saying B and D. Ravi Kumar is saying B. Vaishak is saying B. Okay. Okay, let's check it. So here we have 3 different subspaces, and we are asked which of the following is again as always be a subspace. So here we can get rid of here is that if you have 2 subspaces, then their union might not always be a subspace. So union of 2 subspaces is a subspace if and only if one of the subspace contains in the other. So in general, union of subspaces need not be a subspace. So in that case, in the option A, you have W1 union W2. So this might not be a subspace. And in C, you are taking a sum of 2 subspaces, which is a subspace, but union with W3, which we cannot say that it will always be a subspace. So you can easily mark A and C as wrong. And then for the option D, you are taking subspace W2 and you're removing all the elements of W3 from it. We know that in a subspace there always exists this 0 vector, and when you're removing all the elements from W2 of the W3, when you're removing those elements, 0 does not belongs to W1 minus W3. Hence, it also will not belong to the W1 intersection W2 minus W3. Since the 0 vector does not belong to our subspace, option D is not a subspace. So the only remaining case is option B. So why it is true? Because here also we are removing the W1 from our V, but we are taking the span of elements of V. So if you have any set of elements and you take a span of those elements, then that will always forms a vector space. So B is a correct option because a span of any subset of V is always a subspace. So option B is correct. So shall we move to the next question? Okay, this jumping is first. Okay. So this is a simple question. I hope that you can answer it fast. Consider a set which is some set of polynomials which forms a collection of vectors of polynomials in real field. Then what is the dimension of the subspace spanned by S in the collection of polynomials? So is it 1, 2, 3, or 4? Okay, option 4. There is one doubt in the previous question. So they asked how can if I take a previous case. So here in the span, here 0 is removed. How can it still be a vector space? So here if you take, so what I'm saying is that if you take any collection which might not contain a 0 element, but you can always write a 0 as a linear combination of these elements. So if you take 1 0 0 0 1 0 0 0 1, you can write some combination. If you take the span of this, so you're considering a linear span of some vectors. In the definition of span, we are always considering a 0 in it. So even though you remove this 0 element from it, we can always get the 0 element in the span. That's why when you write the basis, there is no a 0 element in the basis, but still if you take the span of that set, there exists a 0 element. So you don't have to worry about the 0 from this collection.
Yeah, Rosna, let me add one thing.
Uh-huh.
Actually, span is also defined as the intersection of all subspaces containing some set. So, so such type of issues are not there. It will always be a subspace. Whatever you remove, no issue. Okay.
Yes. So the doubt is about the 0. What happens to 0? So that's why I try to.
I think they're asking about if 0 removed, then what happens? Yeah, because these type of doubts are arising because they are thinking of as the set of all linear combinations only. But span is actually being defined as the intersection of all subspaces containing that set.
Yes.
If the set is non-empty, then it will coincide with the set of all linear combinations.
Thank you, sir, for the clarification. Okay, I hope that your doubt is clear. Okay. So many people are saying option. Okay, let me try to. So Shika and Tapan says option C. Let's see whether it's dimension 3 or not. Okay, we have a set S. Clearly, it has 4 elements and it is spanned. So our subspace is spanned by S. So I sometimes write the span of S is L of S. So it's a span of S. It denotes the span of S. Then the dimension of this vector space spanned by S is at most 4 because we have at most 4 elements in S. But I'm not saying that that is the basis of our set, so we have to check whether it is linearly independent or not. So for that, here we can write the x cube plus x square plus x has a linear combination of the remaining ones in this way. X cube plus x square plus x equal to half of these elements. So the basis of our space L of S is nothing but this set. And now, so I claim that this is the basis, but Actually, I have to show that this is a linearly independent set. If you have doubt, if you believe me, then no problem. But if you have doubt, you have to really check whether this is a linearly independent collection of vectors. For that, so how can you check it? Sorry. How can you check it? You can just write C1 times the first one plus C2 times the second one, and C3 times the second one equal to 0. You put C1 inside, C2 inside, and C3 inside, and you gather elements with same degree. Then you will get C2 plus C3 of x3 plus C1 plus C3 of x2 x square, sorry, plus C1 plus C2 of x equal to 0. Here what we meant by 0 is nothing but 0 x cube plus 0 x square plus 0 x. And by equating the coefficients, we get C2 plus C3 equal to 0, which implies that C2 equal to minus C3. And next one is C1 plus C2 equal to 0, which implies that C1 plus C2 is now minus C3 equal to 0, which implies C1 equal to C3. And the last one is C1 plus C3 equal to 0. Here C1 and C3 are the same, which means that 2C1 equal to 0, which implies C1 equal to 0. So you have C1 equal to 0, since C1 equal to C3, C3 equal to 0, and minus C3 equal to C2, so everyone is 0. So this collection of elements forms a linearly independent set, and hence is the basis of our vector space. So it has dimension 3. So option C is correct. Yes. I hope this is easy and everybody got it. So the next question is, there are two different vector spaces, and these vector spaces are the subspaces of a set of all matrices, square matrices of size n. In the first vector space, you have the sum of I over n aij equal to 0. And the second case, the other way around, sum of j equal to 1 to n aij equal to 0. So one is the row sum and another is the column sum. They are the 0. Then what is the dimension of the vector space W1 intersection W2? Okay, Shika says 3, Shruta says 3. Okay. Aparna says 3. Okay, let's see. So what we have, this is 3, okay. So what we have is a matrix which have a lot of entries, and we have an n by n matrix. And we know that in one subspace, the row sum equal to 0. So the sum of the elements in the row, like A11 plus A12 and so on equal to 0. And for each row, this is 0, which means that A11 can be written as the linear combination of the rest of the elements, and A12 can be written as the linear combination of the remaining elements, and so on. A and I can be written as the linear combination of the remaining elements. So that is the one part. And in the similar way, in the other vector space, we know that the column sum is equal to 0. That is, if you have A11, A21 up to AN1, then their sum equal to 0. So in this case also, you can write A11 as a linear combination of the elements of the remaining one, A12 as a linear combination of the remaining one, and so on. So in total, so we need the intersection of these two elements, which means that we are looking for matrices in which both the sum of the elements in the rows is equal to 0, and also the sum of the elements in the columns equal to 0. So in short, what we have is that we have a matrix in which each element of here can be written as a linear combination of the elements of the rest of the things, and each element here can be written as the linear combination of the elements of the rest of the things. So which are the independent set of elements? These entries here are the independent set of elements, because the rest can be written as the linear combination of the elements of this region. So this is nothing but an n-1 cross n-1 matrix. Hence the dimension of W1 intersection W2 is equal to n-1 the whole square. And your answers are correct. So option D is the correct. Yes. Okay, I hope that you understood this question. Let's move on to the next. Okay. Let V be a vector space. So this represents a collection of all polynomials of degree 4 over a field F. Then let U and B be two subspaces, two collections of vectors. The question is whether they are subspaces or not. U is the collection of all polynomials such that P of 6 equal to 0. W is the collection of polynomials which has P of 2, P of 5, and P of 6 equal to 0. Then which of the following is correct? A, U is a subspace of V. B, W is not a subspace of V. C, U plus W equal to U. And D, U direct sum of W equal to V. So here, maybe I will explain what these things mentions. So U plus W means this the collection of so the elements in this set is the elements of the form U plus W, where U belongs to U and W belongs to W. So this is the collection here, and if you have a direct sum, which means that every element in this space can be written uniquely as the combination of the element from U and W. And yeah, these are the main difference between U plus W and U direct sum W. So what do you think about these vector spaces? Maybe I will start with the answer. Let's see whether somebody answers by that time. Okay, first check whether U and W are the subspaces. That's the most easier ones. Yeah, Namika says A is correct. Okay, let's check. So you have U, which is a vector space which contains all the polynomials such that P of 6 equal to 0. So clearly the 0 vector belongs to U, and we check it in the same way. Like if P and Q belongs to U, then their linear combination also belongs to U or not. So I take their linear combination as H of X. Then H of, so what I have to do is that H of 6 equal to 0. That is what I want to prove. Then H of 6 is nothing but A times P of 6 plus B times P of 6. Both of them are 0, then their sum is 0. So H belongs to U. So U is a subspace of V. So Sneha and Shraddha, Anamika, okay, you're all correct. And then we have the other vector space W, which is the collection of P belongs to our polynomial P such that at the point 2, 5, and 6 it should be 0. Clearly 0. The the 0 vector belongs to here, so it's not an issue. We only have to check the linear combination. So in the same way, you define an h of x and evaluate what is h of 2, h of 5, and h of 6, and everything is 0. So W is a subspace of U. So the option B is wrong because it is said as W is not a subspace of V. So the next one is U plus W equal to U. So for that, we know that U plus W is nothing but the collection of U plus the elements is the U plus W, where U belongs to U and W belongs to W. And what we have is that W is a subspace of U, because in the U we only have the condition that P of 6 equal to 0. For W we have P of 2, P of 6, and I think P of 5 is equal to 0. So W is a subspace of U. Then when you consider U plus W, then it will be clearly U itself. So the C is correct. But if you take U intersection W, since W is a subspace of subset of U intersection W is equal to W, which is not equal to 0. Hence, the direct sum cannot be V. So answer D is not true, and we only have the answer A.
Could you repeat once again this part?
So here we have to prove that U plus W, which is how do you mention the elements of U plus W? It is a collection of all elements U plus W, where U belongs to U and W belongs to W. So what I have is the sum of the elements from U and W. But since W is a subset of U, then the part W here is it's actually the elements of U itself. So you're just adding the elements of U again and again. So that only gives you U. So U plus W equal to U. And now we have the case of direct sum of U and W. So here each element of U and W should be written uniquely, and the intersection of U and W should be equal to 0. But here the intersection of U and W equal to W, which is not equal to a 0 set. So hence it cannot be written as the whole union of V. Is that clear?
Yes, ma'am.
So answers are A and C. And I think most of you, what can I say with option C? I think I already explained it. Okay. So the next question is that what is the dimension of a vector space V, which is spanned by the elements A1, A2 up to A100, such that A1 plus A2 equal to 0 and A3 plus A4 equal to 0. And the options are, the dimension is 97, 98, 99, and 100. So this is, I think this is a very easy question. Okay, yeah, I'm getting answers very fast. Okay, most of you are saying option B, which is 98. Yeah, I think you already understood this part. Yeah, we have a vector space V which has 100 elements. So at most, the dimension of V is 100. But here we have some conditions on how the elements behave. We know that A1 plus A2 equal to 0, which means that A1 is depending on A2, or they are each depending on each other, and A3 plus A4 equal to 0, and they are depending on each other. So instead of 100 elements, there are 2 elements which are dependent on the other variables. So we can subtract them from our total variables. So the number of independent variables is 98, and option is correct. Yes, option B is correct. And that was an easy question. Next one is also again next one is again an easy question. Let R be a set of real numbers, and I am taking R square, which is a collection of x1, x2. Then which of the following is a subspace of R2 over R? Option A, the ordered pair x1, x2, where x1 is greater than 0 and x2 is greater than 0. Option B, x1, x2, where x1 belongs to all real numbers and x2 is greater than 0. C, x1, x2, where x1 belongs to x1 is less than 0 and x2 is less than 0, and D, x1 0, where x belongs to R. Okay, many of you said option D. So this is a very easy question. Can someone say why only option D is correct?
Option A and option C are not correct because it will not contain the element 0, 0.
And in option B, does it also contain 0, 0?
No.
No. Only D contains it. Yeah. So this is the easiest case. I hope that everybody got it. And next, this is the last question, and this is also a very simple statement. I hope that you understood the linearly independent and dependencies. So choose the correct statement. Every subset of a linearly independent set is linearly independent. B, every superset of a linearly independent set is linearly independent. C, every subset of a linearly dependent set is linearly dependent. D, every subset of a linearly dependent set is linearly independent. What do you think? Okay, many of you said option A. Yeah, option A is correct, because if you have a collection of linearly independent sets, then any subset of it is again linearly independent. But if you take a superset of a linearly independent set, there can be elements which are depending on it, can be written as a linear combination of the other elements. So B is wrong. And if you have a linearly dependent set, the subset can be linearly independent. So C is also wrong. And every subset of a linearly dependent set is linearly independent. That is also wrong. It can be linearly dependent. So if you have a linearly dependent set, you cannot say much about it. But if you have a linearly independent set, you can say that the subset is linearly independent. Yes, this is my next question. I hope that you understood something about vector spaces.
Okay, thank you, Rosna. You may.
Ma'am, your session was really very wonderful, and I would say that at this period of time, it's a much needed session it was, and it's a kind of one-shot revision for the vector space. We were able to revise the concepts, results, and as well as questions we did, and for me especially, I'm able to revise each and every concept right now, and in such a short period of time, it's really very wonderful, ma'am. And especially for most of them, who all are beginners, for them I think it must be from beginning to mastering the vector space kind of session. So it's really very wonderful. Thank you so much, ma'am. Thank you so much. Thank you, Vinod, sir.
Yeah, thank you,
Good
Shikha.
to hear that it was a useful section.
Rosna, our Shikha is from Jharkhand.
Yes, ma'am. I'm from Jharkhand, and I've completed my integrated M.Sc from Birla Institute of Technology, Mishra, and right now I'm preparing for CSIR exam.
Oh, all the best for your preparation. I hope
Thank
that
you
you will practice them.
Thank you so much.
Yes, others?
Was like a quick revision. So thank you, ma'am. Hoping more classes in future. Thank you for holding such a session. Thank you.
Thank you so much, and thank you for finding time to join this section. I know it's a busy day and everybody was here. That's a great thing.
Yes, others?
Hello, ma'am.
Hi.
I'm Anamika. Thank you very much, ma'am, for the session. And there is only few weeks left for us for IIT JAM exam. So this session was really nice. And as Shika mentioned, this session we need at this last moment. So thank you so much, ma'am, and Vinod sir too.
Thank you so much.
Thank you, Anamika.
Hello, good afternoon, sir. Good afternoon, ma'am. I am Dharmendra Singh from Sasganj, UP. The session was very nice and problem also nice. I want to ask about some reference books and problem books. Kindly please tell and share your PhD experience also.
For the books, for the problems, I usually refer to the previous question papers. I think that's the most reliable things. Other than that, I sometimes refer to the textbooks, the questions from the textbooks, the usual curriculum textbooks, because they sometimes ask concepts behind the questions, not only just tricks of how to solve it, sometimes also the concepts of the idea. So if you don't know the idea, only the tricks, then you might find difficulty in answering some questions. So I also refer to textbooks. But in the last moment, if you don't have much time for preparation, I will suggest you to look at the previous year question papers and try to solve it with the time limit. So that sometimes we know how to answer the questions. The main problem will be the time. We won't be finished by the time. And sometimes we have to left the questions which we think that we could answer, but might take more time. So you should be careful in choosing the questions, which one you want to answer. And so the time management is very important in the last moment. But if you are looking, preparing for next year or something, then I would suggest you to go through the textbooks first, and then also there are many question banks available, and Vinod sir is also conducting questions every question sections every week, so that will be helpful. And about my PhD experience, I would say that it's a bit of a roller coaster experience. See, you can't always say that PhD is very easy or it will go through. There will be some times in which you feel sad or you feel like, am I really able to finish this? But somehow in the end, you will be able to do that. So there will be many times you will feel like I'm stuck, I'm not competent enough, or I'm not good enough, or why these results are not coming in a nice way or something. But if you try till the end, you will be able to do it. So you will know, sometimes you will feel self-doubt, but be confident about yourself and just move forward. Yeah, this is a nutshell of what I have. But I also recommend you, if you get a opportunity to go abroad, I would suggest to do that because there I felt like I have got enough opportunity to mingle with other people. So it's not just my research group I'm working with. I'm working with several people. For example, I'm from Austria, and I'm in a very small group called a place called Graz, which is a very small place. But our research group is collaborating with many other countries. So, for example, Switzerland, Germany, and so on. So, during your time of PhD, time to collaborate with people, go for research stays in different countries. So I have been to Mexico for 2 months, and it's all sponsored by your department or from your funding. So it won't cost you anything, but you will get more exposure, and you can see many people, and you will know many people from your field. So if you want to go into an academic career, one of the important thing is to get connections. So how many connections you have, that is more good to you if you go for next positions and so on. So when I was in Austria, I think I met around 50 or 60 new people, and they at least know my name. So when I write a letter to them or email, I can mention that, oh, we have met in this conference, do you remember me, kind of. Otherwise, when I have to write something to a professor, how I should start? You don't know me and my work. I have to introduce myself, my work, and so on. Maybe they might consider it as a spam or not. But if they know you, they have noticed you once, then it is more easy to connect them. So even if you're here or abroad, try to get more connections during your studies. Even from masters onwards, if you get some chance to attend conferences and meet people, go ahead and meet it. And I know that there will be some sort of shyness inside us to not speak out to the people, especially to the dignitaries of these occasions. but you should overcome it. Otherwise, nobody will remember you. You have to make some impression in their mind. Otherwise, when you meet them next time, they won't remember you. And making these connections is very important in the academic field. And I felt while doing research abroad, this is the one very good thing I can make. I know many people in my area, and you don't have to worry about my language. My English is not that great, but everybody understands. So don't feel like, oh, my English is not good, they won't recognize me. No, it's not like that. They will really talk to you, and you should come out of your shell. You should just try to speak, and then it will automatically will. Yeah. Yeah, this is my small advice.
Yeah,
Thank
thank
you
you,
so
ma'am.
much.
Thank you very much.
Okay, thank you, Dharmendra. Any others?
Hello, ma'am.
Yes. Yeah.
Thank
Oh,
Yes, Neha.
hello, sir. I am Ms. Neha. I am M.Sc first year student in ISIR TVM. This is my vacation time, so I just started to prepare for CSIR NET exam. And this, it's been a lot time to practice some problem because of academics. But this session is very helpful for the thorough revision of vector space. So this session is very good. I just joined first time this type of classes, but I feel this is very good. I revised so much concept today on vector space. So thank you, thank you, ma'am.
Thank you so much, and thank you so much for participating in all the questions. Yes, I saw you were doing very well.
Are you there in our WhatsApp group?
No.
You can join it. It may be useful.
I think I don't have link for that.
See, many of your friends are, your classmates are there in the group. Are you M.Sc first semester?
Yeah, Arya, I think.
Yeah, you can collect my number from Arya, and you can message me. Okay.
Okay, sir. Thank you, sir.
Yeah, okay, sir. Thank you. Yes, Sharada. Yes.
Hello, ma'am. My name is Sharada. Thank you so much for the session. It was very informative, and your PhD experience are also very inspirational, and it's very good to hear, ma'am. Thank you so much, and thank you,
Thank
Vinod
you
sir,
so
for organizing this session. Thank you.
Thank you,
Thank you
Sharada.
so much.
Hello, ma'am. Hello, sir. Thank you so much, ma'am, for spending your valuable time to us. Also, thanks for sharing your experience. Thank you so much, sir, for this session. Thank you.
Thank you,
Thank you
Amrita.
so much.
Yeah. Yes, Anunanda. Yeah.
Good afternoon, ma'am. Thank you, ma'am, for this wonderful session. The way you explained the concept, theories, and questions, and that was very useful. Like explain it in both the ways. It was useful, ma'am, and it was also like a quick revision of what I have studied in class. We have just started the system by this space, and it was very useful to revise it again. And it was I think it's a little more concept for me to ways and in the useful and helpful, ma'am. Can you explain, give us some last minute preparation tips for 3 years?
Last minute preparation. Don't be scared of the exam. You might get tensed, but try to be relaxed, because if you get tensed, you might forget the things you have already known. So our aim is to remember things fast and also be relaxed. So maybe if you can take some breathing exercise just before the exam, that is nice. And also I mentioned before, in order to get over this tension, it is always nice to create an atmosphere before, like an exam. Like take a paper and fix the correct time and mentally prepare that you are in exam hall and try to write an exam and see how you develop, then you might fear less about the exam conditions. Yeah, and I hope that you already prepared very well, so all the best.
Okay, thank you, Ananda.
Ma'am,
Yeah. Yes.
good afternoon, ma'am. I am attending your session for the first time, ma'am, and this was very nice, ma'am. Which means you are explaining in a basic level. That means BSc students can also easily understand your explanations, ma'am. That was kind of your uniqueness, ma'am. Thank you
so
very much, ma'am, for your explanation, ma'am.
Nanda Kumar, please introduce yourself.
Sir, I am Nanda Kumar from Tamil Nadu, St. Joseph's College, and I am doing my PhD.
Okay.
And I am preparing for CSIR Net, sir.
Okay. Thank you, Nanda Kumar.
Thank you, Vinod, sir. You're always an inspirational one to me, sir. Thank you very much, sir.
Thank you for your nice words. Yeah. Anyone else? Any others? Yeah.
Sir,
Yeah, Anila. Yeah, yes, Anila.
thank you, ma'am. Thank you for your section. It was like I just finished my portions, and it was like revision for me. And thank you, sir. Thank you, Vinod, sir, for conducting a section like this. It was very helpful for me. Thank you.
Thank you so much.
Yeah, thank you, Anila. Yes, Aparna, you can speak.
Hello, ma'am. I'm Aparna from Kerala. Your class was very much informative, and you explained each and everything in a detailed manner and in a simple way. Thank you so much, ma'am, for this wonderful session. Thank you, Vinod sir.
Thank you so much, Aparna.
Yeah, thank you, Aparna. I think almost over. Okay. Yes.
Thank you so much, everyone,
Anyone
for
else?
joining for this session.
Yeah.
And everybody was really answering all the questions, so it's very interactive group. So that's also made it more easy to go through the class.